Okay, so well, I kind of messed up the space, so let's try to skip that one because that looks quite similar to the previous example. So let's try to do this example because that one also don't have enough space for me to write. So let's do this one. Well, first of all, I take Laplace transform on both sides of the expression. A slight difference is that the problem has already been structured nicely with the step function involved in it. If it's written in the piecewise function structure, you do need to rewrite it first. So we have Laplace transform of y double prime, which is going to be s squared times Laplace transform of y minus s times y of 0 minus y prime of 0. And then I need to add a 6. So this is the whole coefficient for the Laplace transform y prime, which is s of Laplace transform of y minus the initial value, which is 1, add to 5 Laplace transform of y, and then we do Laplace transform of u5 of t. For unit step function, it's going to be e to the negative 5 of s over s. Okay, so that's us doing Laplace transform. We begin to collect terms. So it's s squared, and then there's a 6s, and then there's a 5. They are all coefficients in front of Laplace transform of y. And then we have the minus s here, and then we have minus 1, and there's a minus 6. So I have minus 6 here, and then we have e to the negative 5s over s. Just to clean things up a little bit, I'm adding s and 6 to both sides, right? So I end up with plus s plus 6, and then I get rid of the denominator because my goal is to find out what exactly is Laplace transform of y. So it's going to be e to the negative 5s, and then it's 1 over s, and then s squared plus 6s plus 5, which we can easily factor because it's equivalent to s plus 1 and s plus 5. Then we do the same thing. I have s plus, my bad, this one doesn't have s anymore. It simply has a denominator s plus 5 and s plus 1. So that's what we end up with. Now I try to do inverse Laplace transform. As you can see, I don't really need to group those terms, two terms together, because one of it has the exponential structure, the other one don't. So this one is a regular inverse Laplace transform setting we should be able to find directly. This one need to use a new technique we learned today. So we try to do inverse Laplace transform of e to the negative 5s, 1 over s, s plus 5, s plus 1. I know for a fact the answer must be having u5 of t in it. Sorry, u5 of t, and then it must be having the f of t shifted by the size of 5. So basically I need to know what's the inverse Laplace transform of 1 over s, s plus 5, s plus 1, so as to get the final answer. So in order to do that, I put my calculation on the side. So this function clearly distinct factors. It's going to be a1 over s, b1 over s plus 5, c1 over s plus 1. Therefore, it's going to be s plus 5, s plus 1. So we have a times s plus 5, s plus 1, b, s plus 1, c, s plus 5. Or for simplicity purpose, what you can do is you can let s being 0. By doing that, you realize your numerator becomes some really nice number, because if s had been 0, this term is 0, this term is 0, then you realize on the left side, your numerator is 1. On the right side, your numerator is a times s plus 5, s plus 1, which is 5a. You know your a is a fifth. And you do the same thing, and basically you choose it in a smart way such that the factors would give you 0. So if you were to let s being negative 1, your left side in this case still 1 because there's no s plug in. Your first term becomes 0, second term becomes 0, your third term c times negative 1 times negative 1 plus 5, which is positive 4, so it's negative 4c. So your c is negative a quarter. And of course, the last case is put the last factor to be 0. So you end up with b times negative 5 times negative 5 plus 1, which is b times -5, -4, which is 20. So your b is 1 over 20. So what you're going to end up with is that this whole function is going to be a fifth of 1 over s, negative a quarter of 1 over s plus 1, and 1/20th of 1 over s plus 5. So I end up with 1/5. Laplace transform of 1 over s is 1. Laplace transform of s 1 over s plus 5 is e to the -5t, and the last piece is negative a quarter, and then it's e to the -t. I got this because I'm keeping my coefficient, and then I take inverse Laplace transform for each piece that's left by finding them in the Laplace transform table. So now I know the inverse Laplace transform of this term. That's my lowercase f of t, which I cannot use directly. I need to use the shifted version of it. So every time I see my t, I change it into, again, double check, just make sure I'm not messing things up. It's t minus c. I'm using that formulation. So I have, well, constant, there's no t here, nothing need to be changed. And there's a t here, it should be changed into t minus the c. C came from exponent of e, so it's t minus 5, and then you minus a quarter of e to the negative. Again, t should be changed into t minus 5. You do need to have a parenthesis to hold it together, so the problem can be structured appropriately. But that's not the end of it. You only solve the inverse Laplace transform of the first half of it. There's a second half of the problem. So you basically do the same thing. You take inverse Laplace transform of s plus 6, s plus 5, s plus 1. You know this is a second order problem. So when you try to do inverse Laplace transform to figure things out, you have s plus 6. Denominator doesn't really matter that much anymore. It's 1 over s plus 5, b 1 over s plus 1. You get your common denominator, but you focus on the numerator. Like I said before, they are distinct roots, so you may simplify your calculation by letting the term to be 0. So this term is going to be 0 if s had been -1. Then s plus 6 on the left side becomes -1 plus 6. Then you have a times s plus 1, b times s plus 1. So you end up with 5 equals 0 plus 4b. So you can find your b quite efficiently. And you may let s be -5 now, so you have -5 plus 6 on the left. You have a times -5 plus 1, and then b times -5 plus 5. As you can see, this term is gone, just like the previous term is gone. So you end up with 1 equals -4a. So a is 1 over -4. So you get both of the coefficients. You can find the inverse Laplace transform. Not yet. You can find it as 4 over 5 inverse Laplace transform of 1 over s plus 5, because you find this constant, and then you find the other constant, which is -1/4. You find inverse Laplace transform of what's left, which is going to give you 5 over 4 e to the -5t and e to the -t. So now you identify the inverse Laplace transform of both of those pieces you need earlier. So you can put together your final answer, which is whatever you had earlier, u5 of t times 1/5, 1/20th, e to the -5t minus 5 minus a quarter e to the -t minus 5. That's the first half, right? And then you add to your second half, which is 5/4 e to the -5t minus 1/4 e to the -t. So this is my final answer. Again, procedure can be slightly tedious, but conceptually it's not hard. The key part you need to pay attention to comparing to previous Laplace transform problems is when you take Laplace transform, you may run into unit step functions, which can affect your calculation a little bit. When you try to take inverse Laplace transform, there might be pieces with exponential structure. There will be pieces without exponential structure. You will be using different formulations to solve them. Hence, you need to separate them out and discuss their inverse Laplace transform one at a time. Okay, so that's all we have for this section. I will be adding a little bit more homework problems into WebWork, so you can practice on that. And also, please finish worksheet number 8. So that's all we have for today.